This slide did not transfer well. As you can see, it looks a little messy. Things didn't line up exactly properly when I uploaded it. However, I did want to leave it here because I think it is in your packet. If you take a look, it just talks about two cases: a process at constant volume, so no work is allowed, and a process at constant pressure, so PV work is the only kind allowed. And it shows the derivation of delta E equals Q minus P delta V to two different equations, and then we eventually get delta E is equal to delta H plus W. Want to introduce H, which is enthalpy. It's the energy which flows as heat for a process that occurs at a constant pressure, and that's the heat that we have at the bottom. Whoops. When we talk about enthalpy, since most of the chemical changes occur at a constant atmospheric pressure, then as we saw a little bit on the previous slide, and I think this one might show it a little better, our heat is equal to E plus P times V. H is the enthalpy, E is the internal energy of the system, P is the pressure, external pressure on the system, and V is the volume of the system. So the change in enthalpy, or delta H, can be thought of as the energy with the work taken out. So the change in enthalpy, which we of course represent with delta H, is the heat obtained or absorbed by a reaction in an open vessel, and where the work portion of delta E is not measured. You can read a little bit more about this in your text on pages 232 and 233. Two important things about enthalpy, which we represent with capital H. The first, it's an extensive property, so it does depend on the quantity of the substance, and then it's a state function, so it depends only on its present state, and it doesn't really matter how it got there, just it's what it started with and what it ended with, not the path to get there. So another state function that we could look at is entropy, and that's something we'll discuss later, and energy. They are state functions, so we look at the beginning and the end, the initial and final, and not the steps in between. A path function, one that does depend on the steps in between, would be work. Read over this practice problems, and you can see other practice problems in this section, pages 232 to 234. And we will work through it together on the next slide. When we're taking a look at this problem, the first thing we have to do is write a balanced equation. So we have 2 Na solid plus H2O liquid gives us H2 gas plus 2 NaOH aqueous. And our delta H becomes part of this reaction. So delta H is negative 367.5 kilojoules. Gives us the temperature as 25 degrees C, which we convert to Kelvin, adding 273 to get 298, and that should say K there. Our pressure is 1.00 atm, so we're trying to find delta U. So we use the equation delta U is equal to delta H minus P delta V. Well, we have our delta H, so we can just plug that in. And then we have to figure out our delta V. Our pressure is 1 to atm, so we could always just plug that one in. We're going to use Pivnert to find our pressure. So we plug in our 1.00 moles, our 0.0821 times 298 all over 1 atmosphere pressure, to get 24.47 liters for our volume. So the next step we have to do is we have to convert the pressure from ATMs to kPAs in order to plug into the equation. And you see my work here doing that. So now if I have the term P delta V, I can take 24.47 times 101.325 kPAs to get 2.479 joules, 2,479 joules, or 2.48 kilojoules. So now I just plug all that information into my final equation that I was working with. Delta U is equal to negative 367.5 kilojoules minus 2.48 kilojoules. The answer is negative 370 kilojoules. Be careful with your sig figs. When you compare two of the answers for delta H and delta U, you can see that these two numbers are very, very similar. We have negative 370.0 kilojoules for delta U and negative 367.5 kilojoules for delta H. So these two numbers are very, very similar. As we talked about in the previous problem, delta E and delta H are very, very similar. Remember, delta E and delta U are the same thing. So this is the case for a system that doesn't involve change in gas volume and our work is 0. So essentially, delta H is equal to delta E, or delta U. So chemists tend to use delta H more frequently because It's very convenient to study processes at constant pressure. An example of something going on in an open beaker, an open test tube, rather than trying to make a sealed container for it. The enthalpy of reaction is found by the following equation. It's kind of funky on here, but the delta H is equal to delta H of the products minus the summation of delta H of the reactants. We have to sum all the delta H's of reactants and all the delta H's for the products, and then we subtract the reactants from the products to give us the total delta H. This is called the enthalpy of reaction. Note the order of this equation. Delta H is the delta H of the products minus the delta H of the reactants. So it's final minus initial. This change in enthalpy, or delta H, is also known as the heat of the reaction if it's at constant pressure. This slide and the next slide look very similar to two slides we had in section 6.1 and 6.2. This is a graph showing the delta H. And in this case, it is exothermic because the products have less delta H, or enthalpy, than the reactants. And so delta H would be negative, just as we talked about with Q. And in this case, it shows the enthalpy, or delta H, for an endothermic process. You see that the reactants have less energy, so the products are gaining energy during this reaction, so the delta H is positive. That's it for this section. Make sure that you take a look at the problems so that you can be prepared for tomorrow. And make sure that you write down any questions that you have about section 6.3. And tomorrow when you come to class, we will be working on the work for 6.3.